Okay, this is the first video for Chapter 9. We're going to look at Sections 1 and Sections 2 in this video. This whole chapter is going to deal with molecular geometry and some bonding theories. Let's start off with some stuff from last year. We've got molecular shapes and Vsepr. So if we look at what we call Lewis structure, which we've already seen this year, Lewis structures are where your atoms are all drawn in one plane. For example, we have CH4, which is a Lewis structure. Notice how this is all drawn in one plane. It is flat from the way it looks. Alright, well then we have what is called Vsepr, which we looked at last year. Remember that Vsepr is that valence shell electron pair repulsion. And remember that's because you're looking at electron pairs repelling one another, and they take this shape based on how they repel. We're talking about only valence electrons, so the name does make sense. So our molecules are taking a shape that minimizes the repulsions of electrons. And there are 5 basic shapes. When you look at these, remember we have bonding pairs, which are your bonds, and we have non-bonding pairs, which are your lone pairs. We'll look at some examples. See the chart here, okay? And you will not get this chart on your tests because you will not get it on your AP test. Well, we have 5 basic shapes. We have the electron domain geometry and the molecular geometry. And we didn't really give this electron domain geometry that name last year, but it's just kind of the overall shape. Whereas the molecular geometry can be broken down to whether you have lone pairs or bonds between atoms. So we've got linear, trigonoplanar, tetrahedral, trigonobipyramidal, and octahedral. And then you break each one down based on how many lone pairs it has, but you still have the same total number of atoms around your center atom. And remember, when we look at these, it's all about atoms around your center atom. Alright, non-bonding pairs there of electrons do take up a larger space and therefore make your bond angles smaller. If we remember when we draw these from last year, you have a triangle that is filled in or some dashes. Remember, the triangle means that atom is sticking out front. Those little dashes mean that atom is in the back. So if we were, for example, to draw that CH4 that we did a Lewis structure of earlier, we would draw how the actual bond angles are, and this would be a tetrahedral because there are 4 hydrogen atoms around the center atom. It is not a 90-degree bond angle. We can actually get a little bit further apart with that 109.5-degree angle. So notice how we draw it so that it has 109.5, or at least more than 90. This H is filled in. It is the one kicking out in front. This H here is behind. You got to think of them, these 2 H's to your left, the ones that here are in red, as in the same plane with the carbon. And so if I were to cut those all in half, they'd each be cut in half, whereas the H with the triangle would be sticking out of the page towards you, and the H with the triangle will be back into the page. And we'll do lots of examples with these in a future lab. So I know I said this bond angle here was 109.5 for a tetrahedral. Well, let's go back and look at all the different bond angles for all of the different possible arrangements. So if you've got linear, remember that linear is just what it looks like. It is 180 degrees apart. When we look at trigonoplanar, that is 120 degrees. Like I said a second ago, those tetrahedrals are 109.5. The ones that are 5, which are trigonobipyramidal, have 2. The top ones are 90, and the ones around the middle are 120, and we'll look at that one here in a minute. When we look at ones that are octahedral, those ones are all 90 degrees. Now you do have to be careful with the ones that are tetrahedral because those are bond angles that are a little more known with the ones that have lone pairs. So this bond angle between atoms here with one lone pair is 107.3 degrees, and this bond angle here with 2 lone pairs is 104.5. Well, we didn't talk about this part last year, which is the expanded octets for molecules that have 2 possible bond angles, and they have certain names to them. Okay, we have what we call axial positions and equatorial positions. So they are named according to where they are. An axial position means that it is along the axis. Okay, so these are the top and bottom of this trigonal bipyramidal or bipyramidal. And you have the equatorial positions, and those are, like it sounds, along the equator. So remember, just like our Earth's equator is around the middle, these ones run in the 120 degrees versus these axial ones are 90 degrees from the equatorial one. So you've got two bond angles there. Okay, lone pairs like to be on the equatorial if they can. And that is because you have a bigger bond angle. So the lone pairs like to take up more space because they are total negatives. So they are totally repelling one another, whereas atoms are only partial negatives or partial positives, so they're only going to partially repel one another, whereas you have a full negative charge when you have electrons. So lone pairs like to be on the equatorial because there's more space. The last thing we're going to look at here are some shapes of larger molecules. Some structures have more than one central atom, and your Vsepr still accommodates these molecules that have more than one center atom. The geometry of each central atom is determined individually and then combined together. We have an example of acetic acid, and we have a ball and stick model here and a space filling model here, either one. This carbon here has 4 things around it, so that is a tetrahedral arrangement, whereas this carbon has 3 things around it, so we call that a trigonal planar arrangement. And it doesn't look like it, but this oxygen has 4 things around it with 2 lone pairs. That is a tetrahedral or a bent arrangement. So there are 3 center atoms there, and each one has its own geometry, which then kicks out the molecules in different directions, and then those atoms interact differently with other molecules based on what's available to interact with.